talked about Fermat's theorem, Rolle's theorem, and the mean value theorem, right? And perhaps most importantly, we defined what we mean by a critical number, right? So the critical number is one at which either the derivative of the function is 0 or the derivative of the function does not exist. So I'll write that on the board. Definition: C is critical number for f if f prime of C is equal to 0 or f prime of C does not exist. So critical numbers basically are either where you have a horizontal tangent or you've got some kind of funny business going on with the derivative. It could be a kink in the graph. It could be a it could be a vertical tangent. Those are your likely contestants there. And okay, so that's a critical number, right? C comma f of C is a critical point. And for what it's worth, f of C is the critical value assuming it exists. I mean, I think the way I've given the definition, it's possible that C. Do you remember last time, Jake? Did I say C was an element of the domain for a critical point? I might have said that. So, okay, so C is a point in the domain. So f of C exists. Fine. Anyway, this is a critical number. And then we discovered the first derivative test. Shows that if you look at the first derivative, you can tell whether a particular critical point is a maximum or a minimum or neither by studying how the sign of the derivative changes going across the critical point. All right? This is called the first derivative test. So, great. And let's look at an example. So, here we have f of x equal to 1/3 x cubed plus 1/2 x squared minus 6x. We're going to try to find critical numbers and graph the function. All right? And that's our larger program. Our larger goal here is to graph functions using calculus, all right? Anyway, so first of all, let's find the critical numbers. What's df dx equal to? So we've got 1/3 of 3x squared, 1/2 of 2x minus 6, which of course is x squared plus x minus 6, right? Now, so as we're thinking about critical numbers here, is there any x for which the derivative does not exist? Well, no. I mean, it's a polynomial, right? So the domain of the derivative is all reals. The domain of the function is all reals, by assumption, right? So to find critical numbers, we just need to look for where the derivative is 0. So critical numbers appear as solutions to x squared plus x minus 6, right? Equal to 0. But this is what? This is x plus 3 times x minus 2 equal to 0. Thus, c equals to minus 3 and c equals to 2. Those are our only critical numbers. find the critical numbers, then we draw the sign chart for the derivative. That will show us where it's increasing, where it's decreasing. And we can also apply the first derivative test to decide whether we have a max or a min at 2 and minus 3. So here's the sign chart for the derivative. Right. And so on that sign chart, we have minus 3 and 2. Those are the two places where the derivative can change signs. The derivative is itself a continuous function, so those are the only places where we're free to change signs. And what we got? Well, plug in 0, you get 3 times minus 2, which is minus 6. So we got minuses in here. These are power 1, so it's going to flip signs when we hit the 0. So from this, I can see, okay, so that's, I'm going to erase this here if that's okay. Just this. Yeah.
Okay, so when you brought like the 1/3 3x stuff, what did you do with the 1/3 and whatnot? Like where did it go when you changed it to x squared plus x?
So I just multiply. So like, you know, 2 over 2 is 3 over 3. That's all good.
So like say we didn't have to multiply it out, that would have been like what you took. Like that would have been like in place of like the x squared plus x6, how you broke it down there.
Yeah. Oh, yeah. I mean, this is the derivative right here, right? I mean, and it's just if I'm going to do, you know, if I'm going to do further algebra on it, it pays to simplify, right? Because once we multiply those out, then it's easy to see how to factor here, right? So I mean, just a general rule of thumb, as we're doing calculus, simplification pays off if we have further algebra to do past the point where we are. You know, if it's the answer and your instructor didn't ask you to simplify, then by all means, just kind of put a box around it, you know. But if you're going to do further analysis like here, it pays off to simplify fractions, yeah. So last time we learned that if the derivative is positive, the function's increasing, right? So from this, I can see, okay, so f increasing on minus infinity to minus 3 and 2 to infinity, right? And f is decreasing on minus 3 to 2. So those observations are helpful as we're drawing the graph of this function, right? And first derivative test tells me what? Two things, right? F of minus 3. What is f of minus 3 equal to? Well, there we have to plug the number minus 3 back into the function, right? So we've got minus 27 over 3 plus 9 over 2 plus 18. So that's minus 9, 9. I think that's 27 over 2. Could be wrong. You know. Oh, math. Let's see here. 27 over 3 is minus 9. Minus 9 plus 18 is 9. So it's 9 plus 9 halves. That's 18. 18 halves plus 9 halves, which is 27 over 2. You know, which is 13.5. Right? Now I'm figuring that out because I want to draw the graph here in a second, and these are important features of the graph. Like the y value when it's minus 3 is important because this shows me that the critical point, minus 3, I'll write over here, minus 3, comma 13.5 is local, no, is at what? Well, I can just say is local what? so at -3, we went from plus to minus, so the first derivative test that says that's a local max. And, I mean, technically, 13.5 is the local max. That's the critical point. F of 2, what's f of 2 equal to? 1/3, 8 times 8, right, plus 1/2, 4 minus 12, which is 8/3 minus 10 is 8. Which is, what, 8 minus 30/3? I think that's minus 22/3. So in other words, the point 2, let's see, minus 22/3 is about what? Minus 7.333, something like that. Is local min. And the reason I know it's a local min is because I look at the sign chart, it goes from minus to plus, right? Which means the function is going down, but then it's coming back up. That's a minimum. So then finally, I can graph this function, right? So let's graph. And can you guys tell me, what else do we do graphically? There's something we can do beyond just calculus, right? We know where it's increasing, we know where it's decreasing, we know local min, local max, great. But we can also do precalculus, right? Which is to say what? Find x-intercepts if you can, right? Find y-intercepts if you can, if they're not too much trouble. And for this one, f of x equals to what? Well, we could factor out x, right? X times 1/3 x squared plus 1/2 x minus 6. Now, I don't know, can you factor that? Get rid of fractions.
Can't you do,
Mhm.
what's the call?
Yeah, I'm pull out a sixth. Where's sixth? If I pull out a sixth, that will get rid of the fractions, right? So basically, I'm taking this, I'm multiplying by 6/6. Multiplying by 6/6, I'm bringing the 1/6 out front, and I'm taking the 6 and multiplying it through. And multiplying the 6 through gives me like 2x squared. 6 times 1/2 is 3. And that's minus 36. It may or may not be anything pretty, I really don't know. Okay, so we could find the zeros if we wanted to, but I'm just gonna kind of go, all right, well, I tried. Nothing popping, I mean, we could, fine, I'll try one more thing. Of course, we could fall back on the what? Quadratic, theorem, quadratic formula here to find the zeros, but to get 36, I could do like a 4 and a 9, or a,
So without that
12 and a 3. So you have tried the quadratic formula and you have verified for me that it's not pretty. They're like decimal 5.05 and okay, so but that is another thing you can do, right? So I'm going to stop right there on that. The larger point here is this much we can say for sure, which is that we go through, this is a point on the graph, right? 0, 0. We can see that much, x equal to 0 is an intercept. And we also know that there's a local max at -3, 13.5, which I'll say is like here. We'll make this 10, make this -10. And 2, comma, -7.33. Like here somewhere is a local min, right? And this is also a cubic, right? So we know that roughly speaking, like big picture, it looks something like this, right? But we can see better now what it does. It is going to do something like this. Right? But we don't have to be ambiguous. These turning points, we know exactly. They're -3, comma, 13.5. And this one over here, of course, was 2, comma, -22/3. That's exactly where those points are. And this function's increasing here, right? Decreasing there, and increasing again. Good question, or? Okay. Now, I'll tell you what. I'm going to do a little bit more on this example before we go on, because I think it will be helpful for us, which is I'm going to introduce the concept of the second derivative. All right, so here's a definition. Get the most out of this example while we're at it. So, definition. If f prime is increasing on, let's say, C to D, then y equals f of x is concave up on CD. If f prime is decreasing on CD, then y equals f of x is concave down, which we'll abbreviate as CD on C comma D. Right? And furthermore, if f, if y equals f of x changes from concave up to concave down at, let's say, x equals to x naught, then x naught, comma, f of x naught is an inflection point. All right. So, now, in precalculus if you want. Here's the precalculus definition of concave up. A function is and this is actually pretty useful. I say this not just because it's nice to have a precalculus definition, but because this is actually kind of useful as you're graphing things, just to kind of check yourself. A concave up something, if you draw a secant line between any 2 points, that's a secant line, right? So check out the difference between the secant line with the concave up versus the secant line with the concave down. See the difference? So the secant line for concave up is above the graph of the function. The secant line for concave down is below the graph of the function. So that's another way you could graphically test whether or not you're looking at something that's concave up or concave down. So what about a line? So if you think about graphs y equals mx plus b, it kind of is outside the context of this discussion. Lines are too simple. They're too boring to talk about concave up and concave down for. You could say that a line is both concave up and concave down everywhere, because it's equal to its own secant line everywhere, right? So it's both above and below the secant line everywhere, because we allow for the equality as we discuss these things. But anyway, okay, so now that we know this idea, my question to you is, can we improve this graph by finding where this function is concave up and concave down? Right? I mean, it looks like it's concave down here, right? It looks like it's concave up over there. Somewhere there's an inflection point. Where is that inflection point? Let's find the inflection point for our example. Can we do it? Well, notice f prime prime of x is equal to what? Differentiate x squared plus x minus 6, we get 2x plus 1, right? So if we set that equal to 0, that gives us a possible point of inflection. In this case, it gives me that x is equal to minus 1/2 is likely an inflection point, right? Draw the derivative, the second derivative sign chart. We have minus 1/2 is the one place where it's 0, right? And where is it plus and where is it minus? Well, that's a line, slope 2, so it's going from negative to positive. We go minus, 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 plus, plus, plus. Indeed, it is an inflection. It is an inflection point because we're changing from concave down, left of minus 1/2, and concave up to the right of minus 1/2. And so, in fact, my graph was actually pretty good because that's the inflection point right there. Right? And I think that's right. It was concave down. Then right here, it shifts, it turns over past this point, it's concave up. That's good? So, I should mention to you also, once you have this idea about concave up and concave down, we can use concave up and concave down to get yet another derivative test, often called the second derivative test. What's the second derivative test say? Let's record this for posterity. Suppose you have a critical number for your function. All right. Suppose you have a critical number. Let's see here. Let f be continuous in, well, let's say mere critical number C. example, where we had a local maximum, the second derivative was negative. Where we had a local minimum, the second derivative was positive, because if the function's concave up and you're at a critical number, that means you've got a horizontal tangent and the graph is bending up away from the thing, it's a minimum. Whereas if you've got a place with a horizontal tangent and you've got the second derivative negative, that means it's like an n, it's bending down away from it, that means it's a local maximum. So it's always kind of catches students off guard, but this is max. F of C is local max. I know, like, you want to say, but it's negative, so should that be a, well, no, that's not how it works. Right? Just think through it. But there you go. Now we have two derivative tests, right? But notice that the first derivative test is more powerful, in a sense, right? There's not a case 3. I don't say, oh, an f prime of c equal to 0 says something. The fact of the matter is, if the second derivative is 0, the second derivative test doesn't tell us anything. All bets are off. On the other hand, for the first derivative test, if we find ourselves with the case that the sign does not change, right? If it goes minus to minus, it goes plus to plus for the derivative at a critical point. For the first derivative test does tell us that it's neither max nor min. There's no such conclusion to the second derivative test, right? Oh, man. You guys gotta stop me when I do something as stupid as that. I have been lecturing. I mean, it probably picked up something, but oh well. My apologies to the, well, you know who you are at home. Okay, so next example. And this is exactly, in fact, this is example 6.1.14 in my notes. Here it is, f of x equal to e to the x plus x. Let's just think about this function for a minute, see what we can say about it with calculus. So what's df dx? E to the x plus 1, right? So the derivative exists everywhere. Are there any critical numbers? So set it equal to 0 for critical numbers. That gives us what? E to the x equals to minus 1. There are no solutions to this equation, right? What do we know about e to the x? E to the x is positive, right? So no solutions. No critical numbers. What about concave up, concave down? Can we say anything about that? How about this? Is this function increasing? Is it decreasing? So if e to the x is positive, right? It's increasing, right? Because e to the x plus 1 which is equal to f prime of x, it's always positive. In fact, it's always, basically the smallest it can ever be is 2, and that's only in the asymptotic sense, right? So this thing is always increasing at a rate pretty much larger than 2, right? So, and if we calculate f prime prime of x, what's f prime prime of x? Apparently just e to the x, right? So that's greater than 0. So that tells us that y equals f of x is concave up on the whole real line. And you could graph this thing. See, because all it is it's the exponential, which we know the graph of, right? And x, y equals x, well, that's this, right? So how would you graph the sum of those two functions? What do you do? We can add functions, right? We just basically just add the values everywhere. Let's see here. So it's going to kind of like asymptotically go to the line y equals x down here. So crudely speaking, it's that blue line. It will track, basically, this function will tend to e to the x. Excuse me, the function will essentially, let me put it in words, y is approximately equal to x for x much, much less than 0, because e to the x goes to 0 as x goes to minus infinity, right? So it's going to track y equals x down there. And then for x going to infinity, it's like basically the exponential plus x. It's just, but it's always concave up, But that's pretty much it. Like there's no critical points, right? So, any questions? Okay. Example 6.1.15. Here I have f of x equal to x times the square root of x minus 1 squared over x minus 1. So this one's a little sneaky. Let me point out that what this is, the square root of x minus 1 squared is the absolute value of x minus 1. And that's a case-wise defined function, right? So that's equal to minus x minus 1 if x is less than 1. And it's equal to x minus 1 if x is greater than or equal to 1. So with that observation in mind, you can see that this f of x is actually a case-wise defined function, right? Is f of 1 defined? Or did I say, I might have defined f of 1 to be something in the, oh, I said f of 1 equals to 1. That was part of my definition in this example. This is for x not equal to 1, I have that. And then part of the problem statement, f of 1, I said was equal to 1. Okay? So my point to you is just that if we look at the square root of x minus 1 squared over x minus 1, this is either equal to minus 1 or 1 for x less than 1 or for x greater than 1. So as I kind of unravel the formula, well, let me not write it up there, I'll write it down here. What is this formula actually? We have f of x. So it's either what? It's either minus x or it's x, right? Because I do minus 1 times x or 1 times x for x less than 1, for x greater than 1. And what else? It's 1 if x is equal to 1. So when you have a case-wise defined function like this, you can differentiate case-wise. But then you have to be careful about where the cases come together. All right, so like f prime of x minus 1, 1, and I suspect the derivative doesn't exist. Right? I'm just going to say does not exist for x equals to 1. Now, the reason I'm going to say that, well, okay, so let me just kind of say that without justification for a second to beg a question of you guys. Is minus 1 a critical number then? Excuse me, is 1 a critical number? Well then, yes, 1 would be a critical number, right? Because it's a place where the derivative does not exist. Is 1 a place where the derivative changes sign? Yeah, the derivative changes sign from minus 1 to plus 1 as you go from before and after 1, right? I mean, we could draw the sign chart. It's minus over here, it's plus over here, so that would seem to say that f of 1, which is equal to 1, by the way, is what? Local, what? Local min, right? So I fished you guys into this. This was a trap, all right? This was a trap. How did I trap you? You're like, well, that seems like the first derivative test that you just said, right? But what was in the statement of the first derivative test? Let's go back. Whoa. I'm trying to unplug my camera. Remember, there's a little pesky little word right here. Suppose f is continuous. The functions we've looked at in examples before this have been manifestly continuous. They've been polynomials or exponentials, whatever. This one, maybe it is, maybe it isn't continuous at 1, right? So, in fact, if you look at this, what's the limit of f of x as we approach? The limit of f of x as we approach 1 from the left is minus 1. The limit as we approach f of x from the right at 1 is 1. Those are not equal. There's a jump discontinuity. In fact, the graph of this is nothing more than y equals minus x, which is this guy, all the way to 1, right? Then it jumps up here. F of 1 is 1, right? And then it does this. So we would not say that that's a local minimum. Because if this is not a local, f of 1 is not a local min. So this is false. Because if you take values near 1, f of 1 is not the smallest value. Right? In fact, the smallest value doesn't exist because you'd like it to be minus 1, but that's not available. In fact, the local minimum here doesn't actually even exist. What can we say about it? We can say that this is an example of why we insist on continuity. In other words, if we have discontinuous function, it does tend to disrupt our theorems here, right? So what I can say positive about it is what you want to do, if you're dealing with a function which is discontinuous, what you do is you break it up into continuous pieces. You analyze each one of those continuous pieces, and then you kind of weave the story together from all those different sub-stories. But you got to be especially careful about wherever there's a discontinuity, because the theorems can be deceiving at such points. And that's why we assume the f is continuous at the start of the first derivative test to deal with this example. So. No, yeah, this function has neither a maximum nor a minimum, despite the fact that it changes sign in the derivative. Yeah. That's the kind of question you might stumble across in like a subject GRE, math subject GRE test. It's that kind of thing. All right, so let us move on to greener pastures here. Example 6.1.16. Here we have f of x equal to x to the fourth minus 12x squared minus 5. So by the way, guys, what I'm doing here is I'm just weaving in, like my notes only have the first derivative here. I'm just going ahead and also doing the second derivative as we're doing the first derivative, just, you know, to kind of make lecture a little bit more efficient. Okay, so great. Calculate the derivative. F prime of x, we've got 4x cubed minus 24x. Calculate the second derivative. F prime prime of x is 12x squared minus 24. All right? So places where the first derivative are 0 are critical numbers. Places where the second derivative are 0 are possible inflection points. Places where the function is 0, x-intercepts, right? Can you factor this function? I mean, maybe. I'm gonna give it a go, and then I'll give up pretty fast if we don't get anywhere. To get that 12, ooh. I mean, if you want to, you could do this. This is x squared minus 6 squared minus 36 minus 5. Completed the square on the square. So, so I group these two together. X squared minus 6 squared, half of 12 is 6, but there's a minus. So you square this thing out, you get x to the fourth minus 12x squared plus 36. So I subtracted 36 to be fair. And so this is x squared minus 6 squared minus 41, which is, by the way, x squared minus 6 minus the square root of 41 times x squared minus 6 plus the square root of 41. Now, the square root of 41 is a little bit bigger than 6, right? So this is irreducible. It's never 0. And this guy, on the other hand, is x minus the square root of 6 plus the square root of 41, x minus plus the square root of 6 plus the square root of 41. Now, to be honest, guys, I'm just messing around. Like, I wasn't actually expecting that to work out, so I think I just got lucky. But my point here is not that you should do this. My point is that gaining information at the precalculus level for this example is a pain, right? You agree? Is something you want to do in time pressure on a test? I mean, probably not, right? But critical numbers, we've got 4x cubed minus 24x equals to 0, right? We can factor 4x out, yeah? Right? And so we've got 4x, x minus the square root of 6, x plus the square root of 6, equal to 0. And so I can draw my number line for the derivative. And I got to worry about square root of 6, 0. And I'm in minus square root of 6, rather. Thank you. And then we can plug in some numbers, right? If x is sufficiently negative, then this 4x cubed term wins and you get negative. Then it changes to plus, it changes to minus again, and then changes to plus again. So from this I can see f is increasing. Minus square root of 6 to 0. And the square root of 6 to infinity. F is decreasing on minus infinity to minus square root of 6 and 0 to the square root of 6. So a lot of times I ask you guys to find the intervals of increase and decrease. That's what I'm doing. Those are the intervals of increasing. Those are the intervals of decreasing for the function. I might also say find the intervals of concavity. Where is it concave up? Where is it concave down, right? So in possible inflection points, potential points of inflection, have f prime prime of x equals to 0. Let's see here. So what was f prime prime? 12x squared minus 24 equals to 0, which is what? X squared equals to 2, right? So what are the solutions to that? Plus or minus root 2, yeah? So my second derivative I just got to worry about minus square root of 2 and square root of 2. Actually, as a point of organization of work, like I prefer to draw the number lines for the function, for the derivative, and for the second derivative all at the same scale, and so they're like stacked. So you can look at them with reference to each other. So like I would rather actually write that down here, just so we can kind of see it. You know, like where's square root of 2? Well, square root of 2 is it's like here somewhere, right? Square root of 6, I mean square root of minus 2, so somewhere in here somewhere. And so like first derivative test tells me where's local min, where's local max. All right. So, okay, great. X squared, 12x squared minus 24 is going to be positive here and here, and it's going to be negative in the middle. All right? And that makes sense because this is going from positive to negative, that's a local max. First derivative test, this is going from negative to positive, that's a local min. Negative to positive, local min. Second derivative positive, both of the places where we found local mins. So it's consistent. Right? Now I suggest we graph, right? So like, where's the concave up? Concave up here, right? Concave up here. Concave down in the middle. There's a point of inflection, actually. That was supposed to be 2. Sorry about that. There's a point of inflection at like plus or minus the square root of 2. So here's a rough sketch. Rough in the sense I'm not really worrying about the y scale so much. So let's see here. It's got a local max. At 0. Right? And at 0, it's minus 5. I mean, that much I can figure out. Let's see here. Then it's doing what? It's increasing, and then it's decreasing. When we get to square root of 2, let me put some markers on here. So when we get to minus the square root of 2, it's supposed to flip from concave down to concave up, right? So we get to about right, like right here, there's supposed to be a point of inflection. It's supposed to kind of turn over like that. And likewise here, it's supposed to kind of turn over like that. Yeah, it's going to kind of turn up. Yeah, turn up. Right. Yeah, I think basically that's what it's going to look like, a W. Yep. See, because it kind of turns over. And what was that? What was here? Yeah, what happens at plus or minus root 6? Those are critical numbers, right? And so like minus 6, you got a local min, right? There's also a local min. Both those are the, whatever you call the bottom of the W. I'm not following yet, but so which one?
So right there. Okay.
Mm-hmm.
That side has like minuses and the other square root of 6 has positives.
Right. So yes, absolutely. But notice what it is, right? It's the derivative.
Yeah.
So this is a sign chart for the derivative. That means the function's supposed to be decreasing to the left, and that function, it is decreasing, right, up to that critical.
Oh, and it goes up as it goes. Okay.
Right. I actually have not drawn the sign chart for the function itself, but you stepped out for a second. I went through this stuff, and what I was told them is like, this is pretty awful. You guys might get it. I don't know. I mean, once you see somebody do it, you probably can do it, right? But you can complete the square on a quartic like this, but that's kind of a fortunate event here. And when you do that, you find out there's actually 2 x-intercepts, one at the square root of 6 plus the square root of 41 square rooted, or minus the square root of 6 plus the square root of 41 square rooted. And those are these 2 points. So like the sign chart for the function itself would look like this, you know. I'm going to call that C2. I'm going to call that C1 because I'm tired of writing them. But right, it's plus here. It's minus in between. It's plus again. But I actually haven't written up until now the sign chart for the function itself. So when we're graphing with calculus, a lot of times we find it convenient to draw the sign chart for the derivative to understand increase and decrease, to draw the sign chart for the second derivative to understand where it's concave down and concave up. And I may or may not actually draw the sign chart for the function itself. It's almost always a good idea to do it for all three if you're trying to make like the best graph possible. But yeah, it's a W. So. What's that? You guys want to see another example? Okay, very good. Let's do another example. Can never have too many examples, right? So again, the theme here is how can we use calculus to improve our graphs? And come next class, we'll probably change the question to how can we use calculus to solve real-world problems, right? And look at some things called optimization problems and so forth. But here's example 6.1.17. So here we have f of x equal to x over 1 plus x squared. All right. And I'm actually going to go ahead and draw the sign chart for this one right off the bat. So this is either